So we've seen that alkyl cuprates, dimethyl cuprate for example, are one class of molecules that can preferentially do conjugate additions. What else can do conjugate additions? Well, it turns out that many things can undergo conjugate additions. Hydroxide ion, under the right conditions, can undergo a conjugate addition. So, taking an alpha beta unsaturated carbonyl compound, like methyl vinyl ketone, important enough intermediate to get actually an acetone acronym, MVK. And if we use the right source of hydroxide, calcium hydroxide, for example, generates two hydroxides. And if we do this at a low temperature, like 5 degrees C, so we don't interfere with the core entropy of this reaction, we can undergo a conjugate addition generate beta hydroxyketone or alcohol. He's doing aqueous workup, obviously. Resulting enolate ion. It's possible to add amines. You could add dimethylamine, for example. Do a conjugate addition. Temperature fairly low. We can generate beta amino. We can add alcohols. If hydroxide can do it, we can certainly add an alkoxide. So alkoxides can also add. The key usually is to do this at low enough temperature that your product doesn't want to dehydrate, right? If you use it at high temperature, generally elimination is favored. You end up getting no reaction. HCN can add in a conjugate addition. So we can add to this alpha beta unsaturated aldehyde. Treat this with sodium cyanide or potassium cyanide, salicylic acid. Generate a little bit of HCN. Propane carbon oxygen. Generating a resonance stabilized carbocation. HCN, amines, alkoxides, hydroxides can all undergo conjugate additions in addition to the conjugate addition of cuprates. And it depends on the temperature, whether it's going to, and the conditions, right? If we use a primary amine and the acid catalysis, generally what we're going to get is an imine addition to the carbonyl compound. But if we use some basic conditions initially with a secondary amine, in this case, the 1,4 addition product dominates. So synthetically, you can be on the lookout anytime your product has a hydroxy or alkoxy group, or an amino group, or a nitrile in the beta position to a carbonyl. A possible way of synthesizing that would have been from a conjugate addition of an alpha beta unsaturated compound. Another species that actually adds in a conjugate addition sense is the solvated electron. By taking lithium solid and liquid ammonia, doing a dissolving metal reduction, can reduce only the carbon-carbon double bond and not the carbon-oxygen double bond. It's a very neat alternative to catalytic hydrogenation that doesn't involve using hydrogen gas and doesn't risk reducing the carbonyl compound at the same time. Remember that what happens when you put lithium into ammonia liquid is it actually just gives up its electron, which is then surrounded by the partially positive hydrogens on the solvent, to form what's called the solvated electron. It's very powerful to use CAG. Because an electron floating around in solution by itself is not very stable. And then, of course, the lithium cation is surrounded by partially negative nitrogens. And since lithium really readily gives up its electron, it's able to give it up to even ammonia. This electron can do a conjugate addition single electron transfer to form a radical anion which then adds a second electron for the solution. Form a dianion. And logically, those two anions want to be in 1 and 4 position, so they're at a maximum distance from one another. The analogy, of course, is taking an alkyne and reacting that with lithium solid and ammonia liquid to reduce the carbon-carbon triple bond to a carbon-carbon double bond. This trans stereochemistry, because of the position, because of those two negative charges, want to minimize their interaction by being as far apart as possible, and of course there's also the steric effect. And the carbon-carbon double bond is not reduced. And remember that in this reaction, because this is a much stronger base than the Evan ion, dianion and the resulting monoanion to generate the trans alkene. This is very strongly basic. So ammonia will protonate this dianion. Equilibrium constant. Very large. But then ammonia will not protonate the enolate ion. Because the anion is more basic than the enolate ion. Okay, about 35 for ammonia. Alpha carbon, alpha hydrogen, which means the equilibrium constant for this reaction is approximately equal to 10 to the minus e. So it protonates the dianion, but leaves the enolate until there's an acid workup. Which means that if instead of putting in aqueous acid, you put something else in solution that reacts with enolates, you can actually trap the enolate and make a carbon-carbon bond in the alpha position using alkyl halide, or an oxygen-silicon bond if you use a silyl chloride. So it's actually a useful way of generating a specific enolate. The other reactant doesn't really care if you generated that enolate ion by direct deprotonation of the carbonyl compound using a base, maybe LDA, or whether you generated it by dissolving metal reduction from the alpha beta unsaturated carbonyl. The enolate is the same, and this enolate can then react TMS chloride to form the corresponding silyl ether. Or it can react with an alkyl halide. Chloride, allyl chloride, to do an SF2 reaction, add chlorine, make a carbon-carbon bond, we have a situation like 2-methylcyclohexanone where treating this with a strong base would generate a mixture of enolates. Way of generating just the thermodynamic enolate beta unsaturated carbonyl compound. You're generating this more substituted enolate. If you started with the alpha beta unsaturated compound from the other side, you would generate just the kinetic enolate, right? And you're only going to generate the enolate that's on the same side as the position of the carbon-carbon pi bond to begin with. And because you're usually doing this at minus 33 degrees, which is the boiling point of ammonia, or lower, so that the ammonia stays liquid, there's not going to be enolate equilibration. And in fact, there isn't any of the carbonyl compound present anyway. This parent carbonyl compound is not present until we do an aqueous acid workup. So there's no possibility of enolate equilibration that we can generate one enolate alone and trap that enolate. So it's a synthetically useful way of generating a desired enolate when direct deprobation of carbonyl compound is not practical. And in fact, it represents a really powerful way. This trapping of an intermediate enolate that's generated by conjugate addition is a way of building up a complex molecule quickly from simple components. The beauty of it is it happens in a single reaction vessel that doesn't involve the isolation and purification distributions. Because anytime you're trying to isolate and purify something, you're subject to low yields and loss of material. So for example, if we start with cyclopentene, this first with a cuprate reagent. And we can attach very large molecules to that cuprate reagent if we want to. So we can potentially bicarbon chain. This would have been made in 2 steps from the corresponding bromine or iodide. By first adding lithium. one reaction vessel. Form a new CC bond by conjugate addition. Add that 5-carbon chain. And then alkylate the enolate. Form another new CC bond. Nobody pointed out that I actually started ketone rather than the aldehyde this time. So this is actually what this should form. And now I'm going to have the second UCC bond from the alkylation. Add this 11-carbon so I start with 2 5-carbon building blocks and 1 11-carbon building block with a phenyl group on it. And I make in a single reaction vessel a large 21-carbon molecule where I've added an alkyl group to the alpha position, and a different alkyl group to the beta position. This one being added as a cuprate, this one being added as an alkyl halide. Hopefully, that's the right molecule. And I've shown E stereochemistry for both the alkenes, but whatever stereochemistry is present in the alkene to begin with is going to be maintained because the reactions occur in that position. There is a large class of biologically important molecules called prostaglandins that have this 5-membered ring with long chains at the alpha and beta position. So this cuprate addition followed by enolate trapping has been used in many cases to make those prostaglandins. It would also be possible to trap this enolate by adding silyl chloride to make a silyl ether, and then do other reactions elsewhere in the molecule before regenerating the enolate with methyl lithium and trapping the enolate later. So if I wanted to do something to this double bond, I could potentially do that. Or if there was alcohol in that group that I wanted to decontact or oxidize up, I could do other chemistry using the silyl ether as a way of protecting carbon. So lots of synthetic utility, the aldol condensation, and the products of aldol condensation, the alpha-beta unsaturated carbonyl compounds. One more particular reaction of alpha-beta unsaturated carbonyl compounds where the conjugate addition is another enolate, called the alkyl addition,